Today we're going to take a look at another operating system designed for the 6800 and 6809 processors. This one is called SDOS, and we're going to run it on this Southwest Technical 6800 computer today. SDOS was created by a company called Software Dynamics. In fact, the name SDOS is an acronym for Software Dynamics Operating System. It came out in 1978, a few months after Flex, and then a little bit before that, of course, DOS 68. Those two operating systems we have looked at in other videos in this series. And what I find extremely interesting about this period in time is how rapidly software is progressing. Just a little over a year prior to this, back in the summer of 1977, Percom introduced their floppy disk system, as well as Southwest introduced their first floppy disk system, the MF68. Both of those shipped with operating systems that were really just clones of North Star DOS over in the S100 world. And it's hard to even call those operating systems. They were really just replacements for the cassette. It was a way to use your cassette software with a disk drive. Not what you'd expect from an operating system. But it was just 6 months or so later that Smoke Signals Broadcasting released DOS 68 that we've demonstrated. And that was a lot more of what you'd expect from an operating system, similar to CP/M. I mean, not a clone by any means, but similar capabilities and similar user interface. And then very shortly, just a few months after DOS 68, Flex came out. And in the end, Flex ended up being the most widely used operating system for these early 6800 and 6809 machines. However, the SDOS operating system was really just a few months after Flex was released. And in terms of how the software is constructed, it's clear that the authors of SDOS had worked with and on the internals of operating systems from mini computers like DEC or Data General. It was a much more sophisticated solution than the implementation of Flex or DOS 68. Now, it didn't really sell that well compared to Flex for a couple of reasons. Number one, with the hardware and the user expectations and software available at the time, operating systems like CP/M and Flex and DOS 68 did most everything you needed. The extra complexity of the bigger features that something like SDOS offered really weren't required, and that additional complexity just made it harder to implement software for and harder to write drivers and support to get it running on different machines. And then the fact that it wasn't tied to a particular computer also reduced its sellability. Back at this time, the market was still driven by hardware, by the computers being sold. Flex tended to go out with most every Southwest Technical 6800 or 09 system. So you immediately had a large user base, and a large user base means a larger software base, commonality for sharing things, newsletters, reports, etc. So that's one reason SDOS didn't catch on quite as quickly, even though it was technically a superior operating system in terms of what a computer scientist would say. All right, let's go ahead and get this booted up, and we'll take a look at what it was like to use it, and we'll demonstrate some of the things we talk about that are a little more sophisticated than what you might have found in Flex, for example. All right, let's go ahead and get this thing booted. We'll power on the machine, give it a reset, insert a boot disk into drive 0, and then a data disk over here in drive 1. Now these disks I created from some disk images that another hobbyist made as he recreated SDOS for us. His name is Roberto, and he got SDOS resurrected from its sources and made it work under his fork of the SimH emulator. I took his work and then made it run here on a real hardware system and made it where it could boot using the disk command, the D command in SWTPC. All right, so we come in here and take a look. We're in SWTPC. And D will boot the system. Very shortly you'll see the banner come up indicating it's up and running. All right, and now it's off on disk loading something called default program. The amount of time you see is the amount of time it takes to load and run default program. By default, the default program is actually the command interpreter that's going to interpret the commands we type here. So for example, this command, files, is already loaded. This is the directory command because it's part of the default program. Here you can see default program. Now default program is presently just SDOS commands. That's the command interpreter. See, they're the exact same size. Default program could be your own program if you wanted. that did some custom application or did some initialization of its own and then turned around and loaded SDOS commands, because this does have a command file capability. That's one of the commands in here. You could say do and then give it a file name of command. So like most of these, you can execute command files. Now, one nice thing about the command files that are supported by this command interpreter is that it also can have labels and branches and conditionals, sort of like autoexec.bat files could do later on. Right, another thing you probably notice immediately is the file names are long. These are up to 16 characters. Extensions aren't strictly enforced. In fact, they're just part of that same 16 characters. Here you can see we have some 4-character ones and there's some 3-character ones. And they do define some recommended extensions. But again, it's just part of the 16 characters, including the decimal point. All right, so this file system uses, instead of linked lists like we saw with DOS 68 and Flex, it uses what are called clusters. And then cluster is a collection of sectors that is optimized for the size of the disk. So in this particular case, we have a small floppy disk. The cluster size happened to be set to 5. There are 5 128 byte sectors per cluster. So the minimum allocation unit is a cluster, and that's 5 sectors in this particular disk case. And you could see that as we boot it up. In fact, let me reboot again. And what I want you to watch is the line that comes up right after the initial banner. 1 second. All right, this 810 Southwest Technical 6800, that actually came from the disk. On every single disk, whether it's a small floppy or a 32 megabyte hard drive back in the day, contains information on sector 1 that tells it how big the disk is, what the cluster size is, what the disk interleave is, a number of other parameters, including this banner that says what's on the disk. So this is a very nice feature in that SDOS itself can support all these different devices and yet not have to necessarily have special knowledge of them ahead of time. And this is something that was a big shortcoming in CP/M. There was nothing on the disk that was formally defined that said what this disk looked like, what the allocation unit was, in that case block size, what interleave was used, if any. And so this is a nice feature in here. All right, so again, files is the directory command. That's just part of this. Copy is part of the command interpreter, rename, delete, the kind of things you'd expect. There's a free command. You'll see these execute very quick because they're already in memory. It's not like DOS 68 and Flex where all of these commands had to be retrieved from disk in order to execute them. There's a user space command, tells you how much space you have in memory for user programs. That's 7,000 hex. I already mentioned the do command for executing command files. There's a version command that'll tell you what version of SDOS you're running. You initiate the debugger from here. Let's see. Of course, we have the copy command, things like that. So for example, here's a program, error message, error maintenance. Here's an error maintenance program. So we can copy that, error maint to error 2. Now this program is 3 clusters long. You see it's done already. So this system feels fast when it does not have to reload the command interpreter because it's already got it loaded, and then it's an efficient file system as well on top of that. So now error 2 is the error maintenance program. And again, as you can see, I can run a file that's not a command built into the SysDOS commands by just typing its name. So this allows you to maintain the error file. The error file is a random file that is a very, very sparse at this point. So here's the actual error file itself. It says it's 202,000 bytes big, 203,000. That's bigger than this whole disk. But it's very sparsely filled. So it's only occupying 17 clusters, which is about 10K. So this file system works very well with sparse files. For example, you can see this. If we do a list from error number 1 through error number, say, 300, you'll see that it's got every record filled for the first 20-something. And then here's a bunch of holes in here, but none of those are using any disk space. Here's another group at 100, and then a bunch of holes. And then here's another group at 200. And these have keys or error numbers all the way up in the thousands. And so if you had that filled all the way between from number 1 all the way up to 1,000 something, yeah, it'd be a 223K file. Notice how long this takes to load. This delay you're seeing here is the amount of time it takes to reload the command interpreter. That's that SDOS commands file. So that's a little inconvenient when you exit from a program that has to be loaded. But once those are in place, of course, doing anything else is then very quick. So I can delete error 2, and it's very nice and quick. If I want to look at a different disk, I just give it a drive number. Now the syntax is D in drive number with the colon. So here we're looking at the second drive in this system. If I want to look at a file, I can explicitly list. It's good for looking at text files. I can list d1 hello.asm. That's this file right here. And that lists it for us. If we want to, what did I do wrong? Oh well, at least a soft error and it recovered, I guess. So there's a small assembly file. Now what's interesting, if you take a look at this small file still took up 2 clusters. So it took up 5 sectors in one cluster, another 5 sectors in another cluster. So that's a lot of sectors, 10 sectors for that small file. The reason is because one cluster is the cluster map for any file. It tells you where all the clusters that make up that file are located on the disk. And then from then on, it then needs multiples of clusters to hold the file. So the minimum for any file is normally 2. There's an exception here, this bad clusters that the operating system accesses directly that doesn't quite follow those rules. But otherwise, the minimum is 2. The first cluster is essentially the directory of all the clusters that make up the file, and then the minimum allocation is 1 cluster at a time. So you'll start with 2. So on a really small disk, it can be inefficient, less efficient than, for example, Flex or DOS 68, which use 128 or 256 byte sectors and could allocate that small a unit. But then as soon as you got to bigger things, especially hard disks, having this cluster ability is far more efficient. And what we'll see in just a minute is that you can actually tune that for the disk you're going onto, how big the clusters are, interleave factors, even step interleave, meaning when I do a step, how many sector times does that take so that I'm probably going to end up in the right spot on the next track and make that more efficient. So it's a pretty cool operating system. You can tell they knew a lot of the details about trying to make things efficient as well. All right, in CPM, you can switch drives. You can do like B:, that would make drive B your default, or you can do A:, it makes drive A your default. Right now our default drive is D0. To make drive D1 our default, the command is default disk and then D1, for example. They like long command names, and the way I type, I don't like that because I make mistakes all the time. But now you can see we're on drive 1 doing our activity without having to type in the D1 anymore. If I want to look at D0, now I have to do D0. All right, this has the concept of device independency. You can copy between any devices. You can treat the disk as just a linear sequence of bytes. You can actually, well, for example, let's take a look here. If I were to copy hello.asm to drive 0, you would typically see a syntax like this, hello.asm to D0. And on CPM and on Flex and DOS 68, it would copy hello.esm to D0 hello.asm. This is actually going to want to copy it to the disk as if it was a serial stream of bytes. So it's wanting to treat it as a device instead of as a file system. And it knows that's probably not what you want to do, so you say no. So here your syntax when you want to do a file copy without explicitly naming the destination is to do a wildcard. This will then copy hello.asm to D0. See how fast that was? It's very efficient. And yeah, and you can do wildcards on your commands here like you'd expect. So I can do files, D0, *.asm, and there's our hello.asm. All right, another interesting thing about this operating system is that it, you heard a lot of activity there, and I'll explain that here with what I'm about to talk about, is that it has a cache. It has a cache it maintains of, I don't know how many sectors or clusters off the top of my head, might be a full cluster for that matter. that helps improve its reliability. That includes writing. So when I did that copy and went to drive 0 and then back to D1, it had to flush some of that cache out, and we could hear some of that activity. And if I do files again, the disk didn't even come on. It's because right now it's all cached. If I was to run anything, for example, let's just go look at hello.asm again. That's gone out and read hello.asm, so now if I do files, it had to go out and access the disk to get this information again. So that's a nice feature, is it's got the ability to really improve performance with this cache, and it uses an LRU, least recently used mechanism, to flush old sectors out. The downside, of course, is that you could end up with corrupt disk if you just yanked a disk. So there's a dismount command that's important to use if you're ever going to remove a disk. Here it's told you how much it's done. I can dismount D1 as well. And you should always do that before you shut down a system or you remove a disk. Now there's a mount command as well, but as soon as you do any operation with the disk, there's an implicit mount. All right, this came with an assembler. It came with the basic compiler. For example, we can assemble a hello. Source file, it asked for it, but I typed it, so it assumes that listing file, you can give it one, or you just hit return or none. Binary file. And here it's allowing me to specify assembler options if I want to, in addition to what might be in the file. Okay, so it's done, and now you'll see a delay here. This is the delay it takes to load the command processor back in. So when you run a program in memory, there is a bit of a delay getting the command processor back in, but it's kind of nice to have that preloaded, because then everything you do feels relatively quick. Okay, so here you can see the hellos. I could do again the wildcard. And so now if we list hello.list, you can see we get a listing of our program, complete with, of course, all the address information and data. And you can run it just by typing. Okay, and again, this delay here is reloading the command processor. It doesn't know whether your program clobbered the command processor or not. It's just going to assume it is. I imagine there's a way to exit a program where you can tell it not to do that, but I haven't dug into that work at all. All right, let's see if there's anything else interesting to get into. Okay, again, the BASIC is a compiler. Here's a program that was written in BASIC called Chess, and there's a calculate program which allows you to just as a demonstration of a basic program. Nothing really new to show you there that you haven't seen in other ones. Let's go back to drive 0. Again, this had the concept of device independency, where I told you could copy a file to a drive number and it would actually write to that disk. The more common use of that would be the other way around. You could copy from a drive number to a file. So for example, you copy from a file, a floppy drive number, and copy it to a file on, say, I don't have a hard disk, but say you had a hard disk on D2, and you could just call it drive0.dat. That essentially does a backup of that whole drive very fast, just a linear sequence of bytes, especially if you had to manipulate it or do anything with it. And you could put it back on with the opposite copy. But more common would be to route things to I/O devices, like the paper tape punches or card readers or paper tape readers or that kind of thing. So for example, one of the common devices that's always there is console. So I could copy console to a file. So now everything I'm typing is going to go into a file. Oh wait, see, now here I messed this up. Copy is a binary option. So it's telling the console device to treat this as a binary file, in which case none of the text I'm typing is going to be converted and use any of the things like Control-Z to indicate end of file. So right now I have no way out of this but to reset the machine. And I could end up messing up the file system. So it shows you how that's a little touchy sometimes. Let me go ahead and reboot here. If you want to do text, you would want to list the console to the test device. So if I wanted to list a file, I would say list and then the file name. So for example, hello.asm. Oops. However, if I did list console and gave it a file name, now what I type is going to test text. Control Z is end of file. So now it's actually written that. If you notice, it didn't actually go to disk. I did not hear a sound. So there's our test.txt. If I list it, you'll see that is in there. Now I do a dismount D0. I think we should hear it start the disk and write that out. I don't know if you could hear it, but I just heard it go out. So now that is kosher and that's all in there. So that's one way to make files. Now, interestingly, Roberto, who made this, created a device called port that he used to get things in and out of the emulation into his file system on the PC. And port does things differently. So for example, if I copied, let's copy hello.asm to port. This is a binary copy. In this case, the port device converts it to ASCII hex. And so there is hello.asm as a bunch of ASCII text. However, if I list hello.asm to port, then the device port that he created, its device driver, just does it as text. And he does the same thing the opposite way. He brings in with a copy. If I copy port to test2.txt, this is expecting binary now. So I could type in 31, 20, 32, 20, 33, 20, 0D, 0A. So that was the digit 1 space 2 space 3 space carriage return line feed. So now, yeah, so 1, 2, 3 and line feed. So anyway, this device independency can be a pretty powerful tool in the end. All right, well, that's a quick look at SDOS. Again, for what most people are going to do with it, it's probably not dramatically different than using Flex in terms of the features it gave you. It had the ability of being fully interrupt driven. It had multitasking ability in the kernel that allowed the operating system to do read-ahead operations, and of course to also do the buffering features and to still allow things to happen very efficiently and quickly. That required writing drivers that supported all of that, which could be done, but it ended up not being done in widespread use. And most people sitting here just using this didn't care about the efficiency that much. In fact, that's always astounded me. I've often thought about making a video about that. Almost all of these systems, other than this SDOS one, for example, I could get a 2-to-1 improvement just by writing a better disk driver in the CPM BIOS or in the DOS 68 system or in Flex, just free. No additional hardware, just software, and suddenly your system's twice as fast. And yet it didn't happen. All I can think is that people were thrilled at how fast this was compared to cassette, and driving down to the computer center and dropping off a deck of cards and coming back 4 hours later to pick up a listing. It was all great compared to that. So they didn't worry about efficiencies. But like I said, that might be another video I do in the future. But anyway, here's a quick look at SDOS. Sorry that I've rambled all over the place, but I threw this one together kind of quick.